garden.
All right.
Back with 4.5, the dimension of a vector space. Theorem 9. If a
No, you go ahead, do it. You got it.
no, it's got to be your classic Southern drawl voice.
Well, so he's just throwing shade.
Oh. You're trying to do his voice. No. I was just trying to narrate. Did it work out well?
We're gonna find out.
All right.
Wow. All right. So a vector space has a basis, and a basis again means an efficient span. All right. We're using those vectors. Any set containing more than n vectors must be dependent. Right. So it's the same question that we're asking. How do we find out whether or not something is independent or dependent? Foolishness. Right. Is there foolishness or is there not? Right. Is there a free variable? Right? That's what we're asking. Okay? Is there a free variable? Yeah. So if that is already a basis, if I have more than that, then n vectors must be independent. Must be dependent, excuse me. And I don't really know. Right? I always have to do work on it. And sometimes I can think about it. I should have told you like what I was doing.
We figure it out.
Yeah, no, I don't know. I mean, I can minimize that.
You press the red button.
Not really. I could have been hiding it. I could have been standing in front of the projector while that happened. All right, so there's the proof. There we go. If a vector space has a basis of n vectors, then every basis of V must consist of n vectors. Okay, so we're going to do some hard stuff at the very end of this chapter. We have to know how to add and subtract. All right, so all we're going to be doing at the end. We're going to be adding and subtracting. Okay, so Selena, you write notes or you doing homework?
World star.
Okay, so. That's what you need to be taking notes right now. Okay? That's what we need to be doing. Unless you want the homework quiz right now. Like this second. And I was talking about you individually, not plural. If I'm talking about plural, then I use my southern drawl and I say y'all. That's how you know the difference between singular and plural use. Everybody knows that. So basis is vectors, independent or dependent. So if B1 has more vectors than B2, then are we talking about an independent? Which one is the independent? So then B1 is a linearly dependent set, which cannot be the case. Because you have more vectors than another one, it's going back to that. And I don't really love this, honestly. N vectors, every basis must consist of n vectors. If you have more vectors, then it has to be dependent. More vectors than whatever we have. So this is a basis. This is just a random basis. So we're saying that B1, for example, has 3 vectors, right? Yeah. And then B2 is going to have 4 vectors. So those 2 vectors cannot be a basis of each other. A basis, it cannot be an efficient span for that one. That's kind of what that is saying. And I don't really love these fill in the blanks ones, but we'll just go through them. If B1 has more vectors than B2, then B1 is a linearly dependent set, which cannot be the case. Right? If B2 has more vectors than B1, then B2 is a dependent set, which cannot be the case. So therefore, they have to be the same. Okay, that is kind of a proof by, I guess it's like the null hypothesis, where we assume the opposite is true, and then we prove that that can't be true. Right? I think that's the null hypothesis. Is that correct?
Yeah.
All right.
I think you empirical evidence.
So if n is spanned by a finite set, then V is said to be finite dimensional. And we'll talk about what that means for spanning stuff. The dimensions of V, written as dim V. Dim V is the number of vectors in a basis. How many vectors do you have? Then is that is spanned by that? What does span mean? What does span mean? Yeah, linear combination, right? There's a pivot in every place. There's a solution for whatever we want to choose. If I choose 126 to be one of those, then it's going to work out. I can get 126. The dimensions of a zero vector space is 0. If V is not spanned by a finite set, then it's going to be infinite. Okay? So, what's the standard basis for P3? How do we write that? Yeah, that's that one. The standard basis is going to be 1, and whatever variable you choose, t squared, and t cubed. So how many vectors do we have in that? There you go. That was a little bit easier instead of all that fill in the blank stuff. Right? We have 4 vectors in here. Right? The standard basis. Good. So those are those vectors. The dimensions of a polynomial, not R, but the polynomial, we have one more thing, and that's what I was trying to say like last class, right? Because I knew it was coming. The standard basis for Rn are those same things, right? 0, 1, 0. Basically, it's the identity matrix mushed together, right? And it's going to be squared. So that's why the dimensions have to have the same number of vectors in that one. So the dimensions of R3 is 3. And just remember, if you have a polynomial, you got to add one more to it. Degree 3, dimension 4. R3, R3, dimension 3. Okay? That's it. Find the basis and the dimensions of the subspace. Now, and how do we know stuff about the subspace? What is the subspace? Zero vector? You can pull out a constant, right? We're good with that. So find the basis and the dimensions of the subspace. So now it's really the same thing, right? What's the dimension of this? 4, because we got 4 variables, right? No, what we're saying is that we are getting that vector. When we add this together, we're just pulling out A, right? Just pulling out A. And we have 1, 2, 0, 3. It's really the same thing as T naught, T to the power of 0, T squared, T cubed, similar to that. So we're getting that with this, and we pull out a B, and we have 1, 2, 1, 0. And we pull out a C, and we have 2, 4, 1, 3. And we pull out a D. So those are those 4 vectors. We have 0, 1, 1, 1. And now I can get any vector. That will be closed in addition. And it will look like that. It just might be a multiple somewhere. Right? I can get out the 0 vector. Right? Are we good? And 0 plus 0 plus 0. It's going to be 0. And it's closed in addition. Because all those things are real. That's kind of important. Right? But it's something that we just have it in there, so it is actually a subspace. Right? So, what do we want? The basis. Here is the basis. The basis is going to be vector 1, vector 2, vector 3, and vector 4. We got 4 vectors, so the dimensions are 4. Right? We good with that? Yes? All right. Contains only 0 vector. Is it R3 though still? One-dimensional subspace. It's a span of V. These subspaces are So the subspaces of a one-dimensional, what is that going to be? Huh? What does it look at? What they're asking for is geometrically, what does this represent? It's just a line, right? It's a line through the origin. Okay? We don't have the zero vector. As long as that vector, that one-dimensional vector, it's just going to be, it's in R3. It's a subspace of R3. We have 1, 0, 0, or 5, 0, 0. What does that mean? We start here and we go out 5. Huh?
If it's one dimensional, why is it a line?
Because it still has movement, right? We still think about that vector as 5, 0, 0.
Because
It's still in R3, yes. All right, a two-dimensional subspace, span of those two vectors, where their U and V are in R3 are not multiple of each other, which means that they're going in different directions, right? They're not on the same line. These subspaces are what? It's going to be a plane through the origin. Okay? Three-dimensional subspaces, blah, blah, blah. Columns, according to the intermediate value theorem. No. What does IMT stand for? Thank you. Okay? It's in R3 now. Because the columns of R3 expand, and that would be, if you actually graph that, that would be what? What would that be? Representation of it?
It's just like
A sphere?
just all 3D points. Yeah.
That's right.
And it'd be like a line of 40.
Right. So let H be a so we start talking about like lines and planes and everything else. We just kind of wave our hand at it and what that means, and it depends on what the variables are. We can't really represent those geometrically, right? We can't. Any linear independent set of H can be expanded if necessary to a basis of H. And again, for the 15th time, what does basis mean? There you go. If H is finite dimensional, then the dimension of H is going to be less than or equal to the dimensions of V. Okay? So what that was saying is that we can have H is a subspace of it. And so we already said that we can think about a line through a plane is going to be a subspace of R3. Okay? Because I'm in the real world, and I can draw a line in the real world. Right? I can draw a plane in the real world, and I can make a box in the real world. Right? It's kind of the way I think about it. So it's a subspace of it. And the dimensions of a line is just going to be 1. A plane is going to be 2. Right? So it's going to be less than or equal to that. But if they are linearly independent, so that is that. Let H span that. H is a subspace of R3. Right? Are we good with that? And what's the dimensions of H? 2. We just have to be able to count in this one. This is just hella easy. 2 is less than 3. That's all that's saying. The dimensions of R3 is just R3. Okay? We could expand that, and we can make another basis. And you have an infinite number of possibilities right there. Right? So, this H thing, whatever, that is a basis. So, that is a subspace, of R3, not a basis of R3. But a subspace of R3. And I can add on another vector to form another basis, to form a basis for R3. This is a basis for R2. And then what would be a vector that you could make right there? There you go. 0, 0, 1. And you can make up a lot of different things. As long as it's not a multiple of that. Right? So any numbers really. It's kind of hard not to make a basis for R3 by adding another vector. Okay? kind of hard to screw that one up. So basis, p-dimensional subspace, the p has to be greater than or equal to 1, linearly independent set of exactly p vectors is automatically a basis for p. Exactly p vectors, automatically a basis for v. Whoops, did I do that right? Yeah, I guess I did. All right, and so again, show that that's going to be a basis for P2, and we've kind of already done that, right? There's really no point in doing that when we did that last class. Is that a basis for P2? I mean, that was like the last thing that we did. It has to be, right? Linearly independent, right? So the vectors, I call it vector 1, vector 2, and vector 3. The vectors are independent, right? And what are the dimensions of that basis? Yeah, right? That's a way to do it, right? And we're good with that? You got questions on that? How do we find the dimensions of a column space and a null space? Right? We have to know that. So that's going to be on the quiz, right? The dimensions of a column, not the dimensions, but the basis or the solutions for the columns and the null. Is this vector in the column? Is this vector in the null? Right? Whatever. The basis set for column space and null spaces. We know how to do that. But suppose, kind of the same thing. So again, we just write that. How do we find? So this is a good quiz question. How do we find? Not the only thing we're adding is that dim thing. That's it. How do we find the dimensions of the column space? Or how do we define the dimensions of? How do you find the null of A? So this half find the columns of A, and this half find the basis set for the null of A. Right? And how do we do that? How do we find the column of A and the null of A? So for both of them, what did you get?
2.
Oh, okay. The dimensions of the column of A is 2. The dimensions of the null of A is 2. But how did you do that? Right. So, but what is the basis? So it did actually define the dimensions, but how did you do that? Like, what did you kind of have to do to find the null of A? That was a little bit harder. So when you Jesus said, what happened? What did you get out? And so it looks like, what did it look like though? Did you do that? 1, 2 what? 1, 2, 0, 4? 0, 0, 1, 0. So the null of A says that A times what vector gives you 0, right? And so we can write that as the free variable. So this has to deal with, and actually says it right in the next part of it, has to deal with the free variables. These are the basic variables, right? And so these, again, are vectors 1, 2, 3, and 4. So we have, so which ones, is that correct? Yes. Which ones form the columns of A? Yes. So the columns of A, the basis for it, are vectors 1 and vectors 3. And so to find the dimensions is just how many vectors do you have, right? And the vectors that form the null of A, we're going to use, vectors 2 and vectors 4, right? No, it does, because vectors 2 and vectors 4 are the free variables, right?
Oh.
Vectors 2 and vectors 4 are the ones that we're using
Oh, for the null value.
for the null of A. Yes, that's for the null of A. And those dimensions are 4. Okay? Yes. But it's not, I'm just going to say, it's not actually vectors 2 and vectors 4. Those are slightly different. Because, or is it? I don't know. It's not. Right? So the vectors that we get out for that, just making sure we're good with that, is what we're saying is that x1, just kind of in quotes, is negative 2x2 minus 4x4. And then x3 is free. No, x3 is 0. My bad. Right? So what we have is we have, yeah. So that is still, even though it spans kind of our 4, it spans our 4, but it is going to be a dimension of 2, because that's how many vectors you got. Okay? We're good? Yeah, because the null of A. Null of A. Okay? It's going to span R4. Yes, sir.
So will you ask us to identify the three variables?
No. Short answer is no. So the dimensions of the column is the number, the dimensions for the column is the number of pivot columns that you have, and the dimensions of the null of A is the number of free variables that you have. Pivot columns slash basic variables. Okay? Are we good? All right. So that's that. And now we're ready to add. And we already know that if we go back to this, this is the short answer for this last section, which is the easiest, or the next, I think it's the next section. I could be wrong. Actually, we're going to, I forget. Basic variables and free variables. And so we kind of had this. This had 4 variables to it. So those two together gives us the number of what? And so 4 is going to represent the number of what? Number of variables, or in a matrix, the number of columns that you have. So basically, every variable that we talk about has to either be basic or free. Yes? Every variable that we have has to either be basic or free. So therefore, that's going to tell us it's a simple formula. This plus this equals that. Okay? Yeah. That is that.